Some of you are asking me how to do the questions that involve using X in terms of a change in concentration along with a container that's greater than 1 litre in size. So I think the first 2 questions I gave you to do are very straightforward KCs, and then the last 5 will involve the algebraic application of how to find the concentrations at equilibrium. Now, if it is a case that you're using algebra, plus you've got the added feature of having a vessel that's larger than 1 litre, you still have to follow the rules. When you get to equilibrium, you still must divide by the size of the container if it's over 1 litre. So what I'm going to do is I'm going to take question number 3 on that sheet, okay? It's the first of the questions that bring you into the algebraic method. I'm going to go through it with you now. If you're having difficulty with the KCs and the algebra and the containers that are greater than 1 litre, watch this carefully a few times and then go back and see if you can try the other 4. If you're still in trouble, get back to me. Send me an email as quick as you can, and I'll then send on another few solutions just to help you out. Okay, so let's have a look at this. This is number 3 in the sheet of questions I gave you the last day. Consider the following chemical reaction or equilibrium established by dinitrogen tetroxide and nitrogen dioxide at a certain temperature T. Write the equilibrium constant expression for the reaction, and then look at the first line of the next part. The value of Kc is 2. Now, when they give you the value of Kc, not only do you write the Kc expression, but you set it equal to 0.2. So therefore, Kc is equal to the concentration of products, which is nitrogen dioxide, raised to the power of its coefficient, 2, over the concentration of the reactant, dinitrogen tetroxide, raised to the power of its coefficient, which is 1. So we don't have to raise to 1. Once the species is there, it's automatically already at a power of 1. And don't forget that because we know the value of Kc, we set it equal to 0.2. Okay? Now, all I've got to do is to use the usual table method to work out the concentrations at equilibrium of both species and then shove them back into Kc. So the 2 species we have are dinitrogen tetroxide and nitrogen dioxide, okay? And we've got 3 things to look at. Any concentrations mentioned at the beginning, the change in concentration as we move towards equilibrium. And it's the equilibrium line concentrations that we're then going to feed back into the Kc expression. Okay, so that's why I always draw a box down there to remind me that these are the figures I'm going to use. Okay, now, do we have any starting information? Well, part C says 1 mole of pure dinitrogen tetroxide was sealed. So you've got 1 mole. There's your start. Now, at the start, there is never any product. Okay, so you always set the products equal to 0, unless, of course, they tell you otherwise. But in most cases, products are 0. The change is not mentioned. No mention about the change, no mention of equilibrium concentrations, nothing further is given. So now we've got to fall back on algebra, all right? And here's what we say. If we start with dinitrogen tetroxide, and that's going to turn into nitrogen dioxide, the dinitrogen tetroxide concentration is going to drop by a certain amount, but we don't know how much. So therefore, we don't have to know how much. We simply say that this 1 mole of dinitrogen tetroxide will drop by a certain amount, okay? Now, don't forget that the change line for all species has to have the same ratio as the balanced equation. And the balanced equation is 1:2. So that means that the x's have to have the same coefficient, meaning that x will be under the reactant and 2x will be under the product. Now, because products are being formed, it's plus 2x. Okay, so that gives me, if we go down the columns, 1 minus x and 2x. However, this is being carried out in a 10 litre vessel. So we now have to divide both concentrations by 10 to make sure that the concentrations are what the square brackets say, in moles per litre. Okay, so always in the equilibrium line, if the container has a capacity or volume greater than 1 litre, divide the species by that particular number. And just a little bit of a hint. If the volumes were the same on equal sides, then you would be dividing the same number of times top and bottom by the same number. So you don't have to worry about the size of the container if the volumes on both sides are the same. Okay? Keep that in mind for maybe some questions that are on later on. However, in this case, we've got 1 volume on the left-hand side, 2 volumes on the right-hand side, so we've got to divide by 10. So we divide by 10, and we then take these concentrations back up to Kc. And here's what we get. We get the concentration of nitrogen dioxide squared. So that becomes 2x over 10 to be squared over 1 minus x over 10. and that's equal to 0.2. Now we've got to algebraically simplify this. Notice that we've got one fraction divided by another. Go back to junior cert. You don't divide by fractions. You multiply by their inverse. So we get, and I'm going to square out both of these top and bottom, we get 4x squared over 100 multiplied by, turn the bottom fraction upside down, 10 over 1 minus x equals 0.2. Now we've got to simplify the left hand side. So 10 into 10 goes once, 10 into 100 goes 10 times. Of course you could further simplify 4 and 10, but I'm just going to leave it like that just for the moment. Okay, so now what do we have? We've got on the top 4x squared, and on the bottom, when we multiply bottom by bottom, we simply get 10 times 1 minus x, and that's equal to 0.2. Now, in order to clear this fraction, I have to multiply both sides by the denominator, okay? And 10 times 0.2 is 2. So just to keep things easy, 4x squared equals, so we're going to bring this over here and multiply it by 0.2. 10 times 0.2 is 2 times 1 minus x, which gives me the quadratic expression 4x squared equals 2 minus 2x. Okay, now rearrange this thing here. You'll end up getting up, bring it over here. 4x squared plus 2x minus 2 is equal to 0. For the very simple reason that when you're solving a quadratic, you solve the quadratic when it's equal to 0. Again, notice all the numbers are multiples of 2, so you may divide by 2 to keep things easy. X squared, 2x squared plus x minus 1 is equal to 0. Now in this stage, you can use the minus b formula if you want, or you could simply say, look, this is easy enough to factorize. 2x squared is 2x by x because it's prime, and 1 can only be 1 by 1. But I have to multiply the outside and inside terms in order to get plus 1 there, so it's going to be plus 2x minus 1. Now, if you're not too sure how to factorize, go to the minus b formula. I'll show you in a moment that it still works. That gives me 2x minus 1 equals 0, or x plus 1 equals 0, which gives me 2x equals 1, or x equals half. Okay, and here you end up getting x equals minus 1. So we've got two possible answers. We've got x is minus 1, or x is equal to a half. So which one is it? It can't be both. Now go back up and look at the change line. The change line is minus the value of x. So if the value of x is minus 1, that's going to become a change of plus 1, which means that the reactance is increasing, which is rubbish. So we've got to reject that, okay? And don't be afraid to write that down as a reject. So you're going to reject that, and you're going to accept a half as the value for x. So now we've got to go back to the equilibrium concentrations, because that's what the question asks. And the equilibrium concentration of N2O4. Well, what is it? N2O4 is 1 minus the value of x over 10. Well, 1 minus the value of x is a half. So a half divided by 10, so 0.5 divided by 10 is 0.05 moles per litre. And the equilibrium concentration of nitrogen dioxide is equal to 2 times a half, which is 1 over 10, which is 0.1 moles per litre. And that's what the question asked. Calculate the equilibrium concentration in moles per litre of each of the gases at temperature. And there they are. So look, that's the third question in that set of questions I gave you the other day. It shows you how to utilize the size of the container when it's greater than 1. If you need any help with the remaining 4, please tell me which question you need help with and I'll send you back the solution. Okay? Don't suffer in silence.